Okay, good afternoon. So this will be our last lecture for this module. All right, and we'll complete the chapter 7 on hypothesis testing, and then maybe do some revisions. We just upload a file. We called it practice. So just for you to have some idea the questions look like. But it's nothing to do with exam questions or exam papers. It just lets you have some idea. And for you to practice. Really practice, right? And the solutions will be uploaded later. Okay? Give you a short time to do it, less than 1 week to do it. So we'll upload the solutions next week. All right? Too busy, no practice, just read the solution. Then defeat our purpose of practice. You're supposed to try to solve the questions. All right, okay. Chapter 7, hypothesis testing. It seems that many of you may have some problems, so confused, so many things. But I would like to point out, basically this is what we need. There are 3 criteria. I keep telling you that, so now I just write it down. Normal distribution or not. Second one is whether the parameters is known or not. Remember, we're talking about normal distributions. All right. The third one is whether you have big sample size or not. So, first of all, chapter 6, confidence interval. So we have these conditions ABC, referring to the top ABC. So yes, yes, and it's a bracket sigma square. And then there is this hyphen. What does it mean? Hyphen means nothing. It's neither yes or no. We don't need the sample size, large or not. So yes for A, normal distribution. Yes for parameter known. What we mean by parameter, because we're talking about one sample, we're constructing a confidence from the mean mu. So that is the quantity that we need to find confidence interval. But there are other things. So the question is other parameter whether we know or not. So in this case, we refer to sigma square. So when I say yes, sigma square, that means in the case that sigma square is known, all right, the other parameters are known. All right, then the test statistics should be very familiar. It's x bar minus mu, the difference between your estimated x bar and the parameter mu divided by sigma over root n, which is the standard error of x bar. Then the next question is, okay, you'll come up with this one, seems reasonable. This quantity, we look at how this quantity behaves. Based on this, we try to construct the confidence law. So the natural question to ask next is, what is the distribution of these test statistics? So we follow a standard normal distribution. All right? Then the confidence law is given by x bar plus or minus z alpha over 2 sigma over root n. So basically it's in the form of x bar plus or minus a constant. You can interpret it like this. All right? This one, okay, it means x bar minus z alpha over 2 sigma over root n mu and x bar plus z alpha over 2 sigma over root n. That's what this notation means. But basically it's just x bar plus or minus a constant times the standard error of x bar. It's in this form. This constant depends on a few things. Depends on the distribution. So it's sigma over root n. All right. Now this is the starting point. Then now we modify the conditions. All right. So what happens? We don't know the underlying distribution. That means we don't know whether the sample are from a normal distribution or not. All right. We don't have this assumption. then we still know sigma square is given. But in this case, we need a big sample size. Why do we need a big sample size? Because of this central limit theorem. So it tells you that x bar will follow approximately normal. All right? So therefore, when I minus the mean divided by the standard deviation, it becomes a standard normal. But I have to put the word approximate. It's not exactly, because we don't know the underlying distribution, so it's only an approximate distribution. All right? This, in fact, all right? So this, again, you can see that is the same same formula for the confidence interval. All right? Why? Because these two are the same, right? So of course the confidence interval will be the same. But the second one is only an approximate confidence interval. When I say approximate confidence interval, means that this interval will cover approximately 1 minus alpha 100% confidence level. Then, so what happens if you don't know sigma? Don't know sigma and don't care about the sample size, be it small or big. But you need normal distribution. So now you replace S by, replace sigma by S. We estimate the unknown standard error by sigma. By sample standard deviation. So now the question is, okay, then what is the distribution of this quantity? So it's follow no more standard normal, but a T distribution with a degrees of freedom n minus 1. So from there, we construct the interval. So again, the confidence interval is in this form. X bar plus or minus a constant, and then this is the estimate of the standard error of x bar. We replace the sigma by S. All right. But now the constant is taken from this underlying distribution. So it is T alpha minus 1, alpha over 2. All right? Then what's the next? Next, of course, is that, what's the next possibility that we should consider? Yes, no, yes. So naturally, we'll think that the next one is no normality population and no knowledge about sigma. And if you don't know whether it's big sample or not, sorry, I don't have answer. So we need a big sample size. So you can see the relationship when your sample size, when you know it is normal distributed, then it doesn't matter whether it's big or small sample, if your population is normal. But if you don't know whether the population is from normal or not, then you need to apply the central limit theorem, so you need a big sample size. So that, in fact, this also needs central limit theorem. All right. So now, because it's normal distribution, so again it's in this form: x bar plus or minus s over root a constant times s over root n. So what is this constant? So we take z out of 2 because it's approximately standard normal. So we take it. All right. So that's it for confidence interval for the mean mu. So now I press the fast forward button. Okay, here explain all this. All right. So hyphen means it doesn't matter. All right. So the sigma square. So we want to draw inference or confidence interval about sigma square. So naturally, if it's from normal distribution, if mu is known, then we should consider summation xi minus mu square over sigma square and sum them up. All right. This will follow a chi-square distribution with n degrees of freedom. Then this is a chi-square n. So I just pick this point and this point. This point I call it chi-square n alpha over 2. This point I call it chi-square n 1 minus alpha over 2. All right? So in other words, the probability of this test statistics, because it follows chi-square, lies between these two numbers, all right, is equal to 1 minus alpha. I just rearrange it so that sigma square in the middle, all right, or the one end of the inequality, so this, it becomes like that. All right. It's just a simple algebra to work on the inequality. So if the mu is known, is not known, then we cannot use this formula because we don't know mu. So we have then use, this is nothing, although I write it here, but it's just summation xi minus x bar square divided by sigma square. So that is the difference between the two. The previous one, we have a mu. The formula have a mu. Basically, it's measure each individual, deviate from the true mean mu, square the difference, all right, and then divide by sigma square and sum them up. Why I have to divide by sigma square? Okay. Because, first of all, that quantity we know that it follows a chi-square distribution. Summation xi minus mu square does not follow a chi-square distribution. You have to divide by sigma square. All right. So I just replaced the mu by x bar, then I got a test statistic, and this follow a chi-square distribution, but with a different degrees of freedom. All right, n minus 1. So I just copy and paste the above formula, change two things, because mu is not known, so I replace this by x bar, and replace the degrees of freedom from n to n minus 1. So we cover the confidence interval for the population mean, and we also cover for population variance. Then the rest is similar. Okay, two samples. We have two samples. And there are two possibilities. One is called paired sample. That means the samples are related. All right? Then in that case, because they're paired, we look at the difference between the two observations from the same pair. And we're looking at the expectation of this difference. So, again, this one is the same as what we just discussed in one sample case, because now you are looking at not two samples, but one sample of differences between x and y. So you can see that I don't assume that I know sigma. Okay, I drop the case that you know this one. All right. So usually we don't know that. That's why I don't include that scenario in the table. Then how about two independent samples? Two independent samples. So we are looking at mu1 minus mu2. All right? So we want to construct the confidence interval for mu1 minus mu2. Okay, so first of all, sigma 1, sigma square are known. Now here, it doesn't matter whether they're equal or not. Okay, if they're known, they're equal or not equal, then still the formula apply. So the test statistic is x1 bar minus x2 bar. Because we're looking at this, so naturally we'll look at the difference of the two sample means as an estimate. Minus is expectation, divided by, what is the denominator? The quantity in the denominator represent the standard error of x1 bar minus x2 bar. All right, so if all standard normal, so obviously this is my test. So this is the quantity, the random variable plus or minus a constant times the standard error. So it's still sort of like in this form. This time is x1 bar minus x2 bar plus or minus a constant times the standard error of x1 bar minus x2 bar. All right, this one is this part. The constant depends on the underlying distribution. And this is the test statistic that we estimate mu1 minus mu2. So it's in that form. Okay, what's the next line? Okay, the next line is when it is not, we don't have normal distribution. So in that case, you really need the sample size to be big. All right, then the test statistic is still the same thing. All right, that's what we have. We have x1 bar minus x2 bar, try to estimate mu1 minus mu2, and then divide by the standard error of x1 bar minus x2 bar. Because we know sigma 1 square, sigma 2 square, you don't use the s1 square, s2 square. If you know the answer, why you want to do approximation, try to guess? You don't. So we have sigma 1 square over n1 plus sigma 2 square over n2 as the variance of this estimator. And what's the distribution? Apply the central limit theorem and the weak law of large numbers. The central limit theorem, approximately normal. So we can see that the same. All right. So in other words, if I want to save my one piece of A4 size help sheet, I can combine these two, exactly the same, except this I call it approximate. Then I just combine these two conditions. Okay? In other words, if you know both have the known sigma 1, sigma 2 square, and the difference is one with normal population, then I don't care about the sample size. But if I don't have normal distribution, then the sample size becomes critical. You have to have large sample. N is big. All right? So, of course, the next one is unknown. But unknown parameters, sigmas. All right, they are not known. But, although we don't know, but we assume that their variance are the same. All right? We know that they're the same, but we don't know what is the value. So in that case, the test statistics, this is a mistake. Two sample. So this is one. Purposely, intentionally, unintentionally do something like that. So you copy without really understanding, so your formula have a 2 there. All right? Don't blame me. You are the final one, the final user, so you have to check whether it's correct or not. All right? I have a disclaimer. It's not 100% correct. Please check it yourself. All right, so it's 1 over n2. I just bring out the estimate as the pooled variance. So what is the distribution? You see, the argument is always very systematic. Once I have this, then I ask what is the distribution of this quantity. It follows a t distribution plus with n1 plus n2 minus 2 degrees of freedom. Then I okay, so it's the same as before. X1 bar minus x2 bar, a constant taken from this t distribution times the estimate of the standard error. Okay, then what's next? No normal distribution, no information about sigma 1, sigma 2. The only thing that you need is big sample sizes. N1 and N2 are big. All right? Then what is the test statistics? It's similar to the one that we have here, except that I replace the sigma 1 square and sigma 2 square by by S1 square and S2 square. And what is the distribution? Because of the big sample sizes, so I have the standard normal. So you can see this is very similar to this one, except that I replace the sigma by sample as sample variance. Okay, then how about sigma 1 square and sigma 2 square, the ratio of the two? How to get a confidence interval? So this one easier. Only one condition. You must need the normal distribution for both populations. I don't care whether, okay, we assume that we don't know mu's. If you know mu's, then it's a little bit slightly different, which we did not discuss. All right? And then we don't care about the sample size. So, now I see there's another mistake here. All right? It should be S1 square over sigma 1 square divided by S2 square over sigma 2 square. All right? Right? This one, just remember this one, n minus 1 S1 square over sigma 1 square. This is a chi-square distribution with n minus 1 degrees of freedom. All right, so similarly, n1. All right, so similarly, n2 minus 1 S2 square over sigma 2 square is chi-square n2 minus 1 degrees of freedom. Right? The ratio of these two follow a chi-square distribution? Follow a F distribution? No. You have to divide by the degrees of freedom. So it's n1 minus 1 S1 square over sigma 1 square divided by n1 minus 1. All right? The whole thing over n2 minus 1 S2 square as sigma 2 square n2 minus 1. So this cancels out. So therefore it follows a F distribution. All right? So this is the one. This is the test statistics. Okay, my mistakes. All right. So this test statistic follow a F distribution. So then you write down probability of the test statistic between F n1 minus 1, n2 minus 1, 1 minus alpha over 2. So this is the point n1 minus 1, n2 minus 1, alpha over 2. So the probability is 1 minus alpha. Then rearrange it so that you have this ratio in the middle. So that's how you obtain it. And just in case you need to get all this F value, only the upper tail, upper probability are given to you. In other words, if this follow a FAB distribution, this point bigger than it is alpha, FAB, the rotation that I use, FAB alpha. All right? That means this is a constant for which a F distribution with A and B degrees of freedom bigger than this constant with probability alpha. But what is this point? So that bigger than this value, this side, is 1 minus alpha. All right? The usual statistics table will not give this one because they assume that you know this knowledge, which I also assume that. All right? This is equal to 1 over F, the reciprocal of FBA alpha. That means you swap the degrees of freedom, your lower end of FAB, all right, 1 minus alpha. When you swap the degrees of them, it becomes bigger. All right, so it becomes F of BA alpha. All right. Okay. Then come to hypothesis testing. Okay. Same condition, same test statistics, but for hypothesis testing, they're a little bit more complicated. There are one-side test and two-side. All right, one side you also have to specify the direction. So, what is the distribution of this one? You notice that I replaced the mu by mu naught because we are testing this null hypothesis. All right, the null hypothesis is you specify the mu, whether you believe that mu equal to mu naught. All right, so that's why I want to understand the test statistics behavior under the null hypothesis. In other words, I want to know when mu equal mu naught how does the test statistic behave. So I have to substitute mu naught in place of mu. So that one follow a standard normal. But I have to quantify that statement. It needs H naught to be true. In other words, we assume that H naught is true. Then this one will follow standard normal. In fact, all our decisions are based on the assumption that the null hypothesis is true. The idea is that, okay, under the null hypothesis, I see something. I check whether this something that I saw is extreme or not. If it's extreme, probably it's not true, the statement, the null hypothesis. All right. So if I say this, the statement is that, okay, this student is very smart, but then all the 5 modules that he take have failed, right? So if it's a smart student, it shouldn't fail all the 5 modules. So in that case, I may suspect that the statement that he's smart may be wrong. I'm not totally saying that he's not smart, but based on what we saw, there's likely chance that the statement is wrong. I have to compute the probability that for average students, what's the chance of fail? It's very unlikely. All right. Maybe it's harder than getting all A's. There are people getting all A's, right? And I believe there are not too many getting all fails. All the modules taken fail. All right. So my point is that the philosophy of hypothesis testing is that under the null hypothesis, we believe that it's true. So we under the null hypothesis find out what the test statistics behave. So if we find that what we saw from our data, all right, under the null hypothesis does not behave like that. So now I suspect something wrong with the null hypothesis. So the whole idea. So for two-side alternative, mu does not equal to mu naught. I compare my test statistic, whether it's too small or too big. So compare with minus Z alpha for 2 and Z alpha for 2. Gee. Yeah. I said another typo, right? Where's the typo? Number 2, right? Here. This is wrong, right? It should be what? Z alpha, right? You have to put all the probability on one side. So this one, this is a copy and paste without thinking, right? So it's Z alpha, all right? Now, what happens if it's not normally distributed, but we still have big sample size, but sigma square is known? So I still use the same test statistics, right? And what is the distribution of these test statistics? Is it normal? Only approximately normal, all right? So, same here, all right? Then, the next scenario is normal distributed, but we don't know sigma, all right? If we don't know sigma, it doesn't matter whether you have big or small sample. You just replace the sigma by S. Then what is the distribution? T distribution with n minus 1 degrees of freedom. You see? Once you set in copy and paste, everything is the same mistakes repeat again. So it's important. Don't make the first mistake. Then you just copy, and then so once your understanding is wrong in the first fundamental step, then the rest will be wrong. All right. So then, if I know nothing about the underlying distribution, I don't know the sigma, but I have big sample size. All right. Because I don't know sigma, so I have to use the sample variance. Hey, do we need to know mu? Remember, our job is to check the statement, whether we make the decision on the statement. The statement state the value of mu. And the statement say that mu equal mu naught. So that's why I substitute mu equal mu naught. So it looks as if I know mu. But in fact, I work it under the assumption that mu equal mu naught. So that's why you see the mu naught there. All right? So that one, what is the distribution? Is it a t-distribution? And the answer is no. Why is it not a t-distribution? It looks like the test statistic, but this is a t-distribution only if the underlying population is normal. Do we know that whether it's normal? We don't know, all right? So, it's not a t-distribution. Then what is it? Take out our heavy weapon, central limit theorem again. And what do you need in order to use the central limit theorem? You need big sample size. And also one thing, sometimes you forget. The central limit theorem, the results of central limit theorem is the X bar. Don't look at the assumption, wow, big sample size, I have 1 million size of a sample, one sample for 1 million observations. Oh, then these observations follow normal distribution. It's not right. All right? So, if your samples are all only 0 and 1, even 1 million, all these 0 and 1s will not follow normal distribution. Only the sample mean will follow normal distribution, approximately. All right, so, okay. So, approximate standard normal, so we compare with the Z. Yeah. All right, variance. So the same here. So here I ignore the case. In fact, this is what we're supposed to discuss for the rest of the chapter 7. So normal population, we don't know the mean. All right, because there are only 2 parameters. We already state what sigma square is under the null hypothesis. What the other parameter, you decide whether they know or not. Here we assume that we don't know. Okay? And it doesn't matter what the sample size is. So the test statistic is S. Oh, you see, it's good to discuss again. So this is also a mistake. What's the mistake? Because I need to substitute the value. I'm asking the distribution, because my decision rule is based on the assumption that the hypothesis is true. So this should be big sigma naught. That means I have to substitute the value of sigma naught square in place of sigma. And calculate it. Yeah. Copy and paste. Okay, should be alpha for one side, all right, not alpha for 2. Then this is what we're supposed to discuss today. We have not covered that. I forget about the notes. So many slides. Here, one table. Summarize everything about this. Okay, pair. Important thing is that you make sure that it's a pair. You still have 2 samples, but the samples are related. That means the X and the Y's are related. They are coming from a pair, same pair. So then you look at the difference. So it becomes 1 sample. So copy everything from 1 sample, and I copy everything. So all wrong here. All right. Okay. So if it is normally distributed, then this will follow a t-distribution. So that's why the critical value is t. But if it's not normally, it's not from a normal population, I need both set of numbers from a normal distribution. Therefore, the difference is also normally distributed. Then in that case, I have to use a standard normal, because this will follow approximately a standard normal distribution. So that's why then I compare minus Z alpha over 2 and Z alpha over 2 for 2 side. For one side, it does Z alpha over 2, or if the other side, then it's minus Z alpha. So we finished the few slides on this paired test. The next one, 2 independent samples. This we discussed before. So normal population, known variance. So now in fact, what I should do, which I did not do it, is to substitute the value of this one. So that's why the test statistics, in fact, does not have this part. Because under the null hypothesis, it is 0. Am I right? Now, let me slap a sub and ask you, if my null hypothesis 3, 1, 2, 3, right? Equal to 3. Can we test this statement? And what is the test statistics? So in general, the one that I wrote down there, follow under normality assumption, it follow a t distribution. Follow a standard normal distribution. All right? This thing with normal and the sigma are known, then this follow a standard normal distribution. But now the question is, what is mu1 minus mu2? All right? So we want to, remember, we want to test this statement. So I have to incorporate this piece of information in my test statistic. So this will be replaced by 3. All right, so your test statistics x1 bar minus x2 bar, see the difference, compare with 3, and see whether it's big or not. But you have to adjust by the standard error. Okay, so just proceed. Okay. And what happens if you don't know whether it's normal distributed or not? Then you have to use big sample. That's why you need yes for big sample. If you don't have big sample, then what to do? I don't know, right? You say. But if your boss insists that you have to give me a solution, okay I give you a solution. Not perfect, maybe not good as well, but I give you a solution. Still use this test statistics. All right. Of course, the problem lies in what is the distribution of this test statistics. So without big sample size, all right, then I may have some doubt what is the distribution. But then I still proceed as using the central limit theorem. All right. So you may, okay, so that's why it's considered as normal. So that's why these critical values are Z. And this is wrong, this is wrong. Right. Okay, so what happens if it's not known? I mean, it's normal distributed, then we just replace the sigma 1, sigma 2 by the estimate SP square. And this follows a T distribution with N1 plus N2 minus 2 degrees of freedom. So what happens if we even don't know whether they're equal or not, then don't bother to find a pooled variance. We just replace each of this one. But I need a big sample size. The previous one, I don't need big sample size, so long as they're normally distributed. So, wrong. Wow. You see, one mistake and cause so many mistakes, right? So be careful, huh? Okay, how about the variance? The test statistics are supposed to be S1 square over sigma 1 square, S2 square over sigma 2 square. But because under the null hypothesis, this ratio is 1. That means sigma 1 square, this ratio simply means that sigma 1 square equals sigma 2 square. Am I right? If sigma 1 square over sigma 2 square equal to 1, then that means sigma 1 square equals sigma 2. Right? So, cancel. So this is my test statistic. Under the null hypothesis, T follow a F distribution with N1 minus 1, N2 minus 1 degrees of freedom. We need the normality assumption for both populations. Okay. Four pages. I'm thinking since the solution of the practice paper is uploaded next week, so you have time to practice. So also need the time for you to prepare your own table. And before I upload it, just talking. I think you want this one, right? How about those watching webcasts? They don't have chance to vote. All right. Okay. Yeah. You don't want to prepare yourself, But if you prepare yourself, make sure that you understand, because you understand it, you prepare it. Okay, if you use it without preparing it, you may misunderstand some of the terms, some of the right. So, like this kind of thing, if you understand it, you see that there's a mistake, an error, and then you will correct it. If you have doubt, whether this is correct or not, then that means you are not well prepared. All right, I will modify it and upload it in an appropriate time. Right. It won't be asked after your exam. After your exam, you throw away all your lecture notes, all your tutorials, all this. Okay, so that is about the. So basically, all this the rest of the chapter is like that. So here is example 4. So we have 12 pairs. So we get the difference, and then we evaluate. This is one side test. When you see the then, it's one side. So it doesn't matter which side, so long as it's consistent. Because I don't know what you define as 1, what is defined as 2. As sample 1 or sample 2. Oh, here is natural. It's method 2 and method 1. So obviously, we are testing mu2 equal mu1 against mu2 higher average, so bigger than mu1. All right. So your test statistics that you consider should be x2 minus x1. All right. In that case, the rest lah. In that case, your test statistics should be, you're looking for big difference. So this will be T, whatever degrees of freedom. Sigma known or not? Oh, we are not given, right? So we have to calculate ourselves. So you have to estimate it. So it's a T, all right? T distribution. T something degrees of freedom, and then alpha. And alpha equal 0.05. All right. So you can see here it is. All right. Oh, my mu d less than 0. Right? Because I use mu1 minus mu2. I use the d is the first one minus the second one. So I'm looking at mu1 minus mu2. So that's why it becomes negative. All right. So it doesn't matter how you label which one is the first, which one is second. All right. Or whether you consider mu1 minus mu2 or mu2 minus mu1. But your alternative must answering or addressing the question that you asked. Here we are saying that mu2 is bigger than mu1. All right. Okay, set alpha and then compute the test statistics. All right, this is the value that you check whether it's greater than it. All right. So this is the test statistics, compute it and got. Okay, so this is the value. Now, so this is greater than, okay, so this number, what is that? Yeah, so we'll reject whenever it's less than minus 1.798. So this number here, this is from the data. All right, so it's compared with minus 1.79. All right, so this is a T distribution with 11 degrees of freedom. This is the point, minus 1.79. whenever it falls here, we reject the null hypothesis. And the chance of this one is 5%. So now we see minus 2.156, which is here, fall in the rejection region, so I reject it. So it's very easy. Okay, then the next few lines here is to compute the p-value. So this one is to use the t-table. I don't have the exact value for 2.156, but I have these two numbers. This number greater than it is 5%. This number greater than it is 2.5%. I'm talking about, because negative is just on the left-hand side. No negative sign is just on the right-hand side. All right? So, in other words, the probability of the test statistics, which is a t distribution with 11 degrees of freedom, bigger than 2.156, all right, is the same as the probability of t11 less than minus 2.156. Am I right? Just draw the picture. This is the t distribution, symmetric above 0. So this is 1.79, greater than it, 5%. So symmetric, you reflect it, put a mirror here, so this is the mirror image. So of course, less than it is also 5%. These two probabilities should be the same. Right. Make it symmetric at 0. So bigger than 2.1 is the same as less than minus 2.1. All right, what I want to say is that, okay, so now I know between these two values, it's between 5% and 2.5%. So let me repeat again. So one approach is to take the, okay, what I know is that the p-value, this value, I don't know the answer, but it must be less than 5. Am I right? It's here then. So what's the probability? Okay, let me write it like this. T11, all right, bigger than 1.79, bigger than 2.156. Compare with this probability. Which one is bigger? One, the same random variable. I say random variable bigger than 2.1. And the other is the random variable, same random variable, bigger than 1.7 and 1.79. So which probability is bigger? Of course, this is smaller. This is bigger, right? So it is bigger. And what is this? This is 5%. So this must be less than 5%. And also compare this with probability of T11 greater than, I'm sorry. Here, 2.1. Okay, so greater than 2.021. Okay, this probability should be less than this probability because this number is bigger than this number. So the chance of greater than it must be smaller. And this one is 2.5%. So in other words, my probability must be between 5% and 2.5%. That is, it's less than 5%. Okay, so I can answer the question of whether to reject or do not reject. If my alpha is 5%, I don't know the p-value, exact p-value, but I know that it is between 2.5% and 5%. Therefore, I reject the null hypothesis at 5%. But if your alpha is 1%, then what's the conclusion? Reject or do not reject? I say that I don't know the answer. Okay, just saying that. Okay, I don't know his mark, but his mark is between 80 and 90. So is it better than a student with 60? I don't know his mark. I can draw a conclusion because it's between 80 and 90. So the same here. The p-value I don't know, but I know that it's between 2.5% and 5%. So if I want to compare with 1%, definitely it is bigger than 1%. So I do not reject the null hypothesis if alpha is 1%. All right. So that may be easier, right? So you just know roughly what is the p-value. Then you can make the decision. Yeah. Okay. So that's how we do it. Okay, so we make the conclusion and we reject the null hypothesis and saying that mu2 really, the method 2 really yield a higher average percentage than does for method 1. All right, how about the variance? So one variable case, one variance case, so we're concerned about this one. So we have already just done it, right? So this is the distribution under the null hypothesis, all right? And so for two-side alternative, we will, so this is the one that I wrote down. So this one, no mistakes, alpha, 1 minus alpha, all right? Okay, so collect the sample. If this is my alternative, then I calculate my test statistics, and then turn out if it's less than this number simply means that he's here. This number means here. So alpha for 2, and this area is also alpha for 2. So it's false here or false here. Either one. Then I will reject it. All right. For one side, it's similar. Okay. Now, so let's look at an example. So this is the sigma naught square, sigma naught no square. Okay, so claim that the life of his battery is approximately normal with this. This is his claim, right? Okay, so we take a sample of size 10, and we want to know whether, okay, this statement is not quite good. The claim should be better than 0.9. That's what is claimed. So we try to look for evidence to reject the status quo. That means it's really have some evidence to support his claim. All right, so we assume that there's no difference. The existing one is 0.9. All right, so now it becomes, we want to find out whether the sigma changed to 0.9. Now remember, this one is the variance. Do you think a big variance is good or not? Do you like a big variance? Right? That's like a, if I tell you, oh, your midterm test, I forgot the average. If the standard deviation is 20 marks, wow. So that you are even one standard deviation from the mean, you are already difference of 20 marks. And altogether we have only 50 marks, right? 90 marks, sorry, 90 marks. 90 marks. So you are, if it's the mean is some number, and then one standard deviation away is already 20. All right, so maybe it's not good, all right? So, but from my point of view, we like that, right? Think of it, if my test paper, everyone got, out of 90, everyone got 75. Then who are good, who are bad, right? I don't know, all right? So if I got it, half or 40% of the students got 74, and then the remaining got 76. I still don't know. All right, the difference is so small, and also majority. So we want to spread out. So in that case, in terms of test or exam marks, we would like to have a little bit more variation. But variation big means that whatever your estimator, all this may not be that precise. All right, we want to have a smaller variance so that our estimator is close to the true answer. All right, so it depends on what you see here. All right, so as a manufacturer, if we find out that the battery, the performance, the life is very big, bigger than 0.9, then I don't like it, right? If you're lucky, you will get one with a longer battery life. But because the variation is big, right? So you may have you may get a battery which has a very much shorter than the expected value. Now, if the variance is 0.1, the standard deviation is 0.1, then you are somewhere around the mean. So it doesn't matter much, right? So whether your battery is good or bad, the difference is not too big. But if it's 0.9, then 0.9 year, almost 1 year. All right? So what I'm trying to tell you is that sometimes you have to understand the practical meaning of all these parameters, the change of the value. So it's sigma equal 0.9 compared with sigma equal to 2.9. One is very big. So which one would you like? As a consumer, I don't like. As the manufacturer, they also don't like. All right? So both of us want a smaller variation. Think of it. If I tell you your computer has a life 2 years, 2 years will be too long. All right? 1.5 years. And the standard deviation is 1.5. Wow. What does it mean? It means that you buy it, then it may already dead. All right? Or maybe go beyond 1.5, all right, times 3 standard deviation, maybe not work for 6 years. All right? That's not very good. So we want it to be a small variation. So you want the product to be sort of consistent. So you want the sigmas to be small. Okay, so we just proceed and test and so on. So I think I can leave it to you. All right? Okay, and next, variance. So I need normal distribution, and I assume the means are unknown. I did not cover the case when mu is known. And I believe for those who are interested, you may work it out how to test, if you understand the rationale behind. All right? If mu is known, then you have to consider this. All right, the other one is yi minus mu2 over sigma squared. Of course, you divide by n and then divide by n, so cancel out. So this will follow a F distribution. The degrees of freedom will be n1 and n2. Don't understand? Forget about it. Because we seldom know about the mean. All right? Usually you don't know mu and sigma. All right, so we just look at it. Wow. So comparing the precision of one measuring device with the other measuring device, and look at, wow. Oh, okay. So you see, here is what I just mentioned. A teacher compared with another one. All right. Of course, in this case, we want the two variants to be similar. Okay, so this is the test statistics under the null hypothesis. So now I want to highlight it. This is the test statistics, the distribution. But for hypothesis testing problem, we are testing this statement. So we substitute this into, that means we look at a particular case with sigma 1 squared equals sigma 2 squared. Substitute it and ask, okay, then what is the distribution of this one? Of course, it's still a F distribution. But remember, you assume sigma 1 equals sigma 2 squared. So in other words, this one follow this distribution is only when sigma 1 squared equals sigma 2 squared. Only you have this. While this one does not require sigma 1 squared equals sigma 2 squared. All right? So I want you to remember that or understand that. So we just work based on this one. Get the two samples, look at the values, see how compare with the critical values. So this is the one, okay. All right, so here's an example. So we have n1 equal to 11, all right, and so we measure the wear, and n2 equal to 9, all right, and for n, so the x bar is 85, and S1 is 4. So this is x2 bar, and this is S2. All right? So assume the two unknown populations are approximately normal. All right? So test whether the two variants are equal or not. Okay? So use 0.1 level of significance. So we want to test sigma 1 equals sigma 2. Set alpha equal to 0.1. And so this value 3.35. Greater than it with probability 5%. You still have to get this number. This number is F810, 0.05, and take the reciprocal. All right? This number, all right, supposed to be F10, 8.95. That means greater than this number is 95%. But this is equal to 1 over F. I swap the 2 degrees of freedom, and then I look at, instead of greater than it is 95%, now greater than this number is 5%, and then take the reciprocal. It's very simple. Huh? Probability of this random variable greater than this number. Let me call this B. Right? So the probability is 0.95. All right? Then, if I take the reciprocal of it, the reciprocal of it, 10 and 8. So this one becomes 1 over B. Am I right? Hey, if 2 is less than 3, what can you say about 1 over 2 compared with 1 over 3? Right? Weaker than it. So the probability is still, so it's 0.95. All right? So what is this distribution? This distribution F10X, so it becomes F810. All right? If you remember, you see everything is from the definition. F10X is a chi-square 10 divided by 10 over chi-square x divided by x. All right? So, okay, so you take the reciprocal, so now becomes like that. So this is F810. So F810 and equal to 1 over F10x, because you just swap the numerator and denominator. Okay? All right, so it's 1,810.05. Because less than this number is 95%, so therefore bigger than this number is 5%, right? So your B is equal to 1 over F810.05. If you're confused, just remember the upper end must be a big number, bigger than 1 usually. The lower end must be less than 1. So how to get a number less than 1? So you take 1 over something. That one is taken from distribution, which is just swap the degrees of freedom. Okay, so that's it. So the decision rule is if F is too big, or f is too small. Then from here, we compute our data. It turns out that it is 0.64, which is not that small. All right. So we do not reject the null hypothesis. That means, based on the data, we don't have evidence to say that sigma 1 squared is different from sigma 2 squared. All right. Okay. Okay. Revision. 20 minutes. Okay. Have you done your revision? Have you prepared your help sheet? No, not yet, huh? Because it's in the second week. The exam is the second week. We still have almost 2 weeks, right? 2.5 weeks almost. All right. Okay. So in chapter 1, what did we learn? All this. We learn about. What do we learn? So we learn about the operation of events. We will talk about, like mutually exclusive events. Talk about events, right? Exclusive events. So it means that the intersection is equal to empty set. And we also talk about complement events. Complement events. So the two complement, the event and its complement should, union equal to the sample space. All right? And then you can think of it. What can you say about A intercept B and A intercept B complement? Are these two mutually exclusive? Of course, because what you have here are all those belong to A and B. This one, all those belong to A, at the same time do not belong to B. So of course, these are mutually exclusive events. So I can put it like that. All right? Mainly because this one. All right. Then what can we say about this? This equal to A. Basically, the idea is that, this A can be partitioned into two parts. Non-overlapping. Non-overlapping. One part is common to B. The other part is common to B complement. So, difficult to see. This helps, but don't use it as a proof. A, B. So this is A. So this is part A common to B. And what about this part? A must belong to A, but it does not belong to B. So put it together. So that's why probability of A is equal to probability of A intercept B plus probability of A intercept B complement. Right? Okay. And yeah. What else? Okay, so there are a few properties about all these operations. All right. But then yeah. So we talk about permutations. So if you have n objects and you try to permute R of them, all right? So you can think of it, you have R boxes, and then each one has, you have n object, you try to fill up. So we write it as, we permute n object, R objects or n object. So it's equal to n, oh, I forgot to mention this multiplication rule and addition rule. Right. Okay. Anyway, the number of ways to do it is n times n minus 1 times n minus 2 and so on. So the formula is n factorial over n minus R factorial. All right? But if the order is not important, then we call it combinations. So we choose R objects out of n objects. So in that case, it is CNR, right? So it's n factorial, n minus R factorial, all right, and R factorial. Yeah, this multiplication rule and addition rule in counting, right? So you can think of it if you have, all right? So suppose I want to go from here to here, A to B, all right? Then if there is so many 2 ways and 3 ways and 4 ways to go. So I asked, how many ways can I go from A to B? So you can think of it, from A, I have 2 choices. All right? Then for each, remember for each of this way, I have so many ways to go. All right? In fact, from here to here, I have 3 ways to go. So from here, I have 3 ways. From here, I also have 3 ways to go to reach this point. So therefore, it's 2 times 3. And then, so therefore, altogether, there's 6 ways to go from here to here. Why 6 way? Because this is 1 way, 2nd way, 3rd way, and so on. And this is the 1 way, 2 way, and 3 way. So altogether, there are 2 times 3. Then, from here onwards, each of this path will have another 4 ways to do it. All right? So in other words, I have 4 ways from here, and then I have 4 ways to do it. Another way, I also have 4 ways. So basically, I have how many times? 6 times of them. So I multiply by 4. So that is the way that we look at multiplication rule. Remember, it's each of the possible, at each point, there's so many ways that you can do. All right? And then the next point, you also, for each possible combination, you can have so many other ways to do it. All right? But if I go from here to here, all right? So if I go from here to here, all right? Okay. All right, finally, we arrive here. Now this one you cannot use multiplication because here start from here, I have 2 ways to go. But for this way, I have so many other ways. But while for this way, there are only one path, basically from here to here to here to here to reach this point. So you cannot multiply. So you can only add. So this one way times, there are 2 ways here, times 2. All right? In fact, okay. Then for each of this one, I also have one way, so in fact, just count may be easier. All right. But my point is that you multiply, make sure that each one in the two of the options, there are also three. Each will have all three ways to go. So you have this multiplication rule and addition rule. Then we have this essence of probability, which you should be aware of that. All right, but the most important is to define the probability of an event A. So we have this number of outcomes belong to A divided by the number of. So that's one way to get the probability of event A. Count how many outcomes favor to event A divided by the total number of outcomes. All right. Then we start with this probability. So probability A intercept B is equal to probability A plus probability of B union. All right. Because these two parts double count the probability A intercept B. And if A is a subset of B, that means the number of outcomes here is less than the number of outcomes here, then probability of A is less or equal probability of B. Okay. So suppose I have these two events. Take a person who is married. All right. Select from the population, take one. All right. Okay. In this population, okay. So count how many of them are married. All right. And so what is the probability of A? The probability of A will be the number of people married divided by the total number in the population that I'm on. Right. So divide. Okay. This one is the number of married divided by the number of persons that I'm looking at. Okay, how about event B? Married and smoking. Right? Okay, so what can you say about A and B? Is A a subset of B? Or B a subset of A? Or they are not related? Which is a subset of what? A is a subset of B. Or B is a subset of Y. Yeah, because married and smoking. Okay, it's very simple. Right? The first one, A, has only one criteria, married. The second one has two criteria, married and smoking. All right? You have to fulfill the two criteria. Right? So if you want to get a job, you need a CAP to be about 4, and at the same time, you need to be pretty. Okay, CAP about 4 is not good enough. You have to be handsome and pretty. Then that means more strange, right? I mean, I change it. I'm not handsome. All right. But what I'm trying to say is that the more conditions that you apply, then your set, the number of elements satisfied the condition will be smaller. So of course, B is smaller than A. But we are talking about the same population, right? Those belong to B, married, they also belong to A, right? I have to stress that I'm looking at the same population. So whenever they're married, they belong to A, all right? But if they're married but not smoking, they do not belong to B, right? So therefore, B is a subset of A. Therefore, probability of B is less than probability of A. Less or equal. Less or equal. Okay, so I want to emphasize this. If probability of A, if a set probability, okay, if A is we know that probability of an empty set is 0. All right. So if probability of A equal to 0, does it mean that A is an empty set? I purposely trick you. Think of it. I toss a die. Right? Can I get a 7? The probability is 0. Only normal die like 1 to 6, right? So you cannot get a 7. But if I say that, okay, let me define my set is 7, 8, 9, 10. Oh, I have elements in this set. In this event. The event is getting a 7, 8, 9. That's an event. But what is the chance getting this event? 0. So I want to emphasize that. Probability of empty set is 0. Probability of A equal to 0. But it does not necessarily mean that A is an empty set. All right? You can have a set not empty, but the chance of getting it is equal to 0. Yeah. Okay, I don't think I have much time. But let me just mention about the topics. So we also cover the conditional probability of A given B. All right? Probability of A given B, so it's equal to probability of A intercept B divided by probability of B. All right? And before that, we have something called total probability. It's very simple. Maybe draw a picture. All right? This is my event that I am interested in. But before that, I partition this S into various of AI. Okay, too complicated. Let me make it easy. I partition into A and A complement. Right? Only two parts, not overlapping. Then I look at the B. So, the probability of B is equal, I'm talking about total probability. So it's equal to probability of A, B given A times probability of A intercept B plus probability of A complement intercept B. Right? We have just mentioned it before. And then this one is equal to probability of, now, I need A and B. I can have A first, and then multiply, according to this definition, is equal to probability of B times B given, is probability of A, all right, times probability of B given A. That means we go through A first and then get to the B. But there's another path, you get through B complement and then go to the A. So, plus probability of A complement times probability of B A complement. So, in other words, it's like this. We start from here, get to A complement. Then this one, I can get to B or B complement, B or B complement. So in order to get B, I can go through this path. In order to get to B, I can go through this path. So this is the first path, this is the second path. So we write it like that, in terms of conditional probability. All right. And what is it? I think this is chapter 1. Oh, independence, very important. Independence events. So it's probability of two events are independent. All right. Independent events are. So two events are independent if the intersection is equal to the product, or the conditional probabilities is equal to the no condition. It doesn't matter whether B has occurred or not, it won't change. Then we say that A and B are independent. All right? And there's random variable. Wow, these random variables. So random variable basically is work on numbers. So there are a bunch of numbers for discrete case, and then we're talking about the corresponding probability of the random variable. So random variable has two parts. One is the value. The other part is the probability associated with it, or the probability density associated with it. For discrete case, the range, the gaps among the possible values of x, like for example, 0, 1, 2, 3. And the simplest random variable. What is it? Simplest, I cannot have one value. So the simplest is to have two values. Arbitrarily, I take it 0 and 1. So only two values. Then I have the associated probability. So probability of x equal to x. So this is p, 1 minus p. So this is the simplest random variable. Takes two values, each one with a corresponding probability. All right. So it's a very good example to illustrate the idea of probability. We set a value with the corresponding probability. Make sure that the probability sum up to 1 or integrate equal to 1. All right. Then we also have the CDF. Oh, at this point, I think many of you still very confused about this CDF thing. Okay, so yeah, if you are given okay, this is a CDF. Is it a discrete random variable? Okay, first of all, understand this first. What is f? What's f minus 1? I don't see anything there. No minus 1 here. It's 4 in this region, so f minus 1 is 0. F 0.5 there. Again, I don't see any 0.5 there, but it's mentioned here. So this is equal to 1x. And what does it mean? It means probability of the random variable x less or equal to 0.5. Less or equal to 0.5 is equal to 1x. Okay, then how about f 0.4? 1 over 8 also, right? Well, it's false here. 1 over 8. So this is probability of x less or equal to 0.4. How come the two probabilities are, these two are the same? Because it goes collect all the probability until you reach 0.4. What you collect is only 1x. And then you move to 0.5, you still did not collect anything, any probability. So that's why the cumulative probability is still the same. So in fact, this is a step function. All right? Go to 0, 0. But once you reach 0, you jump 1x. And then you go all the way to 1. Before you reach 1, you still remain at 1x. But then once you reach 1, then you jump 3x. This is 3x. So basically, it's a step function. All right? So you have to understand, this is cumulative probability. So in other words, between 0 and 1, before 1, there's no probability there. All right? And then after, from 1 and before 2, there are also no probability there. So in this reflect that it is a discrete probability, discrete random variables. All right? So some of you, based on this one, very careful, work out the PDF, a probability function. X takes the value 0, 1, 2, 3. And then work out the corresponding f of x. And then answer the question, what is the probability of x, let's say, between 2 and 0.5, for example? Ask this question. So you go back to look at this, and then, well, but in fact, you can answer the question from here. So this one means f, is this correct? Cumulative probability until you reach and equal to 2, subtract the part that it reach up to 0.5. Is it equal to this one? It's very clear whether it's equal or not. This means probability of x less than 2 minus probability of x less than 0.5. Correct or not? No. Because if you subtract this part, it will include x, the probability of x equal to 0.5 into it. All right? This is 2 and this is 0.5. No. All right? This is 0.5. So you are subtracting. Okay. Unfortunately, because, okay, strictly speaking, it should be less or equal to 0.5. Because you are subtracting out the probability of x equal to 0.5. All right? So, is this F2? No. F2 is x less or equal to 2, so it's a number slightly less than 2. Then minus F.5. F.5 is here, so it's 1x. F2 minus is not here, it is here. So therefore it's 3x. So it's 3x, all right? 3x minus 1x. So if I ask this question, it may be easier, but if I ask this question, then what is this probability? Okay, so follow what we just mentioned. So it's equal to probability of x less than 2 minus probability of x less or equal to 1. Right? So what is probability of x equal to less or equal to 2? 3x, right? And what is probability of x less or equal to 1? It's here. Also 3x. So answer is 0. How come you have x between 1 and 2? Not equal to 1, not equal to 2, and the probability is 0. Is it obvious? You only have probability at 0, at 1, at 2, and 3. Now you're somewhere between the 1 and 2. Where got the probability? No probability. All right. My point is that you just follow the definition, you will get the answer. All right. If you work out the probability function, the little f, you can also get the answer. But make sure that you understand that, okay, x between 1 and 2, that means it's not including 1, not including 2. Somewhere in between, you collect all the probability. And there's nothing for you to collect. So the answer is 0. All right? So I hope you understand this one. And make sure that you understand it's big F and small f. Big F is the cumulative probability. And the small f for discrete, it will be the probability at x equal to a particular value. For continuous, it will be the density function. And many of you make a mistake in the midterm test. In fact, I mentioned that probability density function. That means for continuous, can be bigger than 1. Because it's not a probability, it's a density. All right? I don't know whether you remember. All right? So, between 0 and half. All right? So I want it to be uniform. So this area has to be 1. So therefore the height has to be 2. Your density function has to be 2. So in that case, it's a simple example to illustrate that it is. Density can be bigger than 2. Because the range is so small, the whole area has to add up, integrate equal to 1. So therefore you must have a very tall, big density function in order to get the probability equal to 1. All right? So PDF can be bigger than 1. Sometimes, not always. All right? But probability function, that means for discrete random variable, that must be between 0 and 1. All right? Okay, I'm sorry we don't have time. So you do your own revision. Prepare your help sheet. All right? One piece, right? Two sides, right? So this time, last time you two sides, this time you also have two sides. All right? Don't copy everything. All right? Don't make it so smart. One piece of paper have 16 pages of notes in it. You try to squeeze. Don't do that. All right? 2 pages should be good enough for you to write down the important information. Oh. Okay, if you have any question, you want to see me a consultation, you send me an email. But don't wait until the last minute. All right.